Okay, let's go over your homework from chapter 21A. And this is the last time we're going to do this way. Um, because of the way we're finishing this year, we're going to be hitting highlights of 4 chapters, 21, 23, 27, 28, I believe it is. And I'll be doing this a little differently. So I just wanted to warn you of that. So right now, let's go over the homework that you had for this chapter. And it was, first one was number 1. And the question was, can you obtain isolated poles by breaking a long magnet in half? And the answer, of course, is no. What you get is instead 2 smaller magnets, each with 2 poles. So you can't isolate the poles just by breaking it in half, because it just doesn't work that way. We'll talk a little bit more about why that is in a moment. Number 6. How can you distinguish ferromagnetic steel from paramagnetic aluminum? And the answer is fairly straightforward. Steel, which is ferromagnetic, is strongly attracted to a magnet, whereas aluminum, which is paramagnetic, is very weakly attracted. The words ferromagnetic and paramagnetic both specifically mean something. Ferromagnetic means that it's naturally magnetic like iron. Paramagnetic means that it has some magnetism but not much, which is kind of related to number 7. Bismuth has a relative permeability of 0.99983. Is this element ferromagnetic, diamagnetic, or paramagnetic? And this is diamagnetic because its permeability is less than 1. Diamagnetic is actually anti-magnetic. It gets pushed away by a magnet. So you have your 3 basic types of materials. Ferromagnetic material, which is very strongly magnetic. Paramagnetic is slightly magnetic. And diamagnetic is anti-magnetic. So you have these 3 types of materials, which then leads you to question number 8. If you want a strong magnetic field, in what kind of material should you generate the field? And the answer, of course, is a ferromagnetic material, because ferromagnetic materials are very magnetic. So if you want a strong magnetic field, you want to use a ferromagnetic material to do that. Okay, number 9 says, what is the best model for explaining magnetism today? And this is really interesting because magnetism is still not understood very well. And so they give us this. The domain model is the best model, and this involves the alignment of the magnetic moment of atoms or molecules in domains within the material. So it's really about aligning atoms and molecules. Atoms and molecules have some built-in magnetism because of their orbital spins, and that built-in magnetism because of their orbital spins, if you line them up in what they call domains, so they're little like sections of these lined up, then you have magnetism. And so that's why some materials, when you run electricity through them, you can line up the atoms. Ferromagnetic materials automatically line up, just naturally line up. But other materials can be made to line up if you run electricity through them. And actually, I had in college, one of the jobs I had in college was recharging magnets by putting them on an electric contraption that you turned it on, and you could put the magnets back together. Because what happened was a bar magnet gets dropped a lot in the lab, and as you drop it, it actually knocks the magnetic domains out of alignment. And so if you put it on the electricity and run electric current through it, it realigns the molecules or atoms inside the bar magnet. So anyway, that's what I did. I did that in college. All right, number 10. Why does a magnetic compass point north? Because the world's north pole is a south magnetic pole, and of course opposites attract. So the north pole of the compass points towards the south magnetic pole, which is the north pole of the world. Number 11. Are the Earth's magnetic poles at its geographic poles? Explain. And the answer is no. The axis of the source of magnetism is not aligned with the axis of the rotation of the Earth. So whatever makes the Earth a giant magnet, that axis, north-south, is not the same as the rotation of the Earth. About 5-degree difference, I believe, is what the answer is. All right, number 12. What is magnetic declination? Interesting, the answer here, this really long, complicated answer, but the book had a very simple one. It's the angular difference between true north and magnetic north. So it's the difference between if you pointed towards true north, which is the north pole of the world, like you want to say United States instead of world, of the world, and where your magnet points towards magnetic north, the difference between those two is your magnetic declination. And that's going to vary depending on where you are on Earth. If you're in the right place, those two actually might line up if you happen to have it be a straight line between you and those two. Or it could be very dramatically different. And in fact, number 13 gives us a question about that. In what direction does the north-seeking end of a compass point when the compass is placed at the north geographic pole? Well, of course, it points towards the magnetic north pole, which happens to be south of true north. So if you the angle of the magnetic declination, is going to be very large when you're sitting at the North Pole and it's pointing south. Number 14 asks, then, what direction does the north-seeking end of a compass point when the compass is placed at the north magnetic pole? And the answer is, well, technically straight down, but in practicality, it just points randomly in horizontal directions because, if you have a compass, it can't point itself downward. But it's being drawn towards the straight down, so it just kind of goes whichever direction. Number 15, what keeps harmful charged particles from the sun from reaching the Earth's surface? And the answer is that it is our magnetic field. They are trapped or reflected by the Earth's magnetic field. So as harmful particles try to enter the Earth, they're caught or trapped by the Earth's magnetic field. In creation, we talk about the fact that the Earth's magnetic field used to be larger and used to be stronger, and that would have protected us from more of those harmful particles from the sun, which might have caused longer life. All right, number 16. What causes the auroras? And I kind of try to simplify this. Some of the charged particles that are trapped in the Van Allen belt, which is from the magnetic field, escape, and that causes showers of charged particles that interact with the atmosphere and produce light. So this is, like I said, kind of a simplified, but this is what causes both the aurora borealis and the aurora australis, which you're not going to see that one unless you're in the southern hemisphere, of course. But that's what causes those, what we call the northern lights usually. All right, now for time for some true false. Number 26. All magnets have both a north and south pole. And of course that is true. There is no monopole. Every magnet has a north and south pole. Number 27. 1 Tesla is approximately the strength of the terrestrial magnetic field at the Earth's surface. And that's false. And the best answer I could come up with for where this came from, because I don't remember this question specifically, is the yellow box that says that the terrestrial magnetic field at the surface is between 3/10 and 6/10 of a Gauss, and that's not equal to a Tesla, because a Gauss is like 10 to the 5th Gausses to a Tesla. So those are not the same. All right. Number 28. A magnetic field is not affected in any way by the material in which it is located, and that is clearly false. Ferromagnetic materials will hold a magnetic field much better than paramagnetic or diamagnetic. It makes a huge difference what kind of material it is. Number 29, the strength of a magnet depends not only on the dipole moments of the atoms, but also on their orientation, and that is absolutely true. Remember the idea of domains. So they have to have magnetic moments, but they also have to be lined up. So that's true. And number 30, magnetic declination over the surface of the Earth is relatively constant from one decade to the next. And that's not true. It does actually change over the years. Okay. All right. Now, you have a review page. If you didn't get your review page to go over your homework, that's fine. Grab your review page now. There's one of the things I want to do differently for the rest of the year. I want to go over your review pages as we're going through the actual material. So grab your review page and for chapter 21. And in the concept section, the beginning of the concept section, the first question is, why isn't a monopole real? And basically, I kind of gave this as an answer. It's not taken from a book or anything, but it's because even down to the atomic level, the magnetism seems to be the orientation of two things. It's an imbalance within the atom, which creates a magnetism, which means that there's always a north and south. That's what causes it to. It's about an imbalance of things, and so it's inherently, you can't have a single particle of it. And in order to have a monopole, you have to have a single particle of excuse me, a single particle of magnetism, and that doesn't seem to be that even down to the atomic level. It's an orientation of two things, not a single thing. Okay, so what happens when you cut a magnet in half? And of course, you get two shorter magnets. And the last question is magnetic declination the same everywhere on Earth? And absolutely no. It depends on your orientation to the two poles. So if you were in line, so that you were standing facing the magnetic pole and right behind it would be the North Pole, then it would be straight up. It would be 0 degrees. If you're at the North Pole, geographic North Pole, and it's pointing towards the south, towards the magnetic North Pole, that would actually be like 180 degrees. Well, that's kind of a weird angle, so it'd be straight down. But the point is, you're actually going to have it. It varies greatly depending on your orientation to the two poles. Okay, that's all I wanted to cover from the review page specifically at this point. Tomorrow we're going to look at the rest of what we're going to look at in this chapter.